And then I want to show you that this idea is basically what a chemical bond is. Right? This is all related to chemical bonds. Let's see. So now we're going to do chemistry that's slightly more in my area of authority than ATP and glucose here. Slightly. So say we have, here's a complicated molecule where A is going to respond to B. There's a physicist molecule. Okay, I gave you two bodies. That's already like massively complicated. And let's think about what happens. We're going to say this is fixed at the origin, and this one moves in X. Okay? Now, normally, like I said, we wouldn't give you the horizontal axis. But here, it's your first one. We'll give you the horizontal axis. Okay? And we just have to think about what interactions happen when these two things start to get close to each other. Here, let's see. So let's draw the energy. Often we don't use U. We just say it's the energy. We don't need to call it a potential. It's just the energy. And we say, okay, here is the axis for moving A and B around. And when they're really far from each other, there's no potential. Say they don't interact, right? If they're a mile apart, there's not going to be any potential or any energy difference between them. But if they start to get close to each other, they're going to be attracted to each other like this. Now, why are they going to be attracted to each other? That depends on what they are and what kind of a bond we're making, right? So if we're just going to make some van der Waals, DLVO, whatever force, it'd be easy to explain. But if we're going to make a chemical bond, like a covalent bond, why do they stick together in a covalent bond? Right? It's the force F complete shell. There's freshman physics chemistry right there. Right? They want to complete the shell, the valence, yada, yada, yada. Some quantum mechanical force is making that want to happen. Right? Is this what scalar teaching with scalar is? I don't know. Okay. So that would, then you'd say, well, then why don't all the atoms in the world stick together? Oh, they don't, because there's another interaction. See, I wrote a force here, right? I didn't write an energy. There you go. In physics, we don't worry about the difference. One, same thing. Force, energy, same thing. Right? So what about this? But what if they get too close? This is the energy of the Pauli exclusion principle. Also quantum mechanics stuff. Two quantum particles can't exist in the same state at the same time. And if you try to force them to, they'll push back really hard. Right? Again, quantum forces really electromagnetic forces. But then the question is, what happens when you add these? So when you have a bunch of energy diagrams and you want the total, you just add them. Right? So if I add those, what do they look like? Far away, nothing's happening. And then for a while, it really wants to complete the shell, but it gets too close. Whoa, like that. Whoa, like that. And okay, so now if I'm at atom B, where am I going to go? Once atomic friction sets in, I'm going to land right here. Right? So this is the bond length right here. That's how long the bond is. Because the origin was a position of A, and this is where B goes, so that's the bond. Right? So here's the origin, like that. So you can do this for lots of different, this is sort of just pretend chemical bonding forces and interactions. You can do it for others. And now I realize I missed a page. Yeah, let me tell you one thing real fast. You need it for the homework? Okay, sorry.